Thank
Okay.
you.
Thank you, Tamur, for the introduction and also inviting me to give this opportunity to present myself virtually. So, my name is Shahid. I'm working currently at Institute of Telecommunication, Portugal. We have associated lab with University of Aveiro, and this lab is funded by European Commission, Nokia, and Altis Labs from France. So today I will going to talk with the 6G vision requirement, technical challenges, and standardization. So I will not going into detail of mathematical analysis or algorithm that you can find in my paper. You can easily browse my profile over the internet. So here the main idea is more interactive session where you can see research challenges for the future along with some nice picture, and hope so you will find this presentation exciting and help you to find a direction for the 6G. Okay, so today the agenda is following. I start with 5G progress, but I will not go into detail of 5G. I have a separate presentation on 5G, but this is a long backstory now. So I mostly emphasizes on 6G. I just give you a brief introduction on 5G here with the technologies which we used. And then I will talk on mega trend towards 6G and services classes and scenarios, requirement, and then candidate technologies and timelines and business model. So part one is the 5G progress. So before start the 5G, so we just have to go to the brief architecture, which we have now starting with the 4G and 5G more or less same, but of course the technologies and the new component is added, but this is the high level architecture. So we have the customer which want around some data rates or around some services, for example 19 gigabit or maybe more. And then we need a spectrum. This is called the blood of any network. Without that we cannot communicate. And then we have the G node B base station, E node B, depending upon the which generation you're talking about, the name is changing. And then we have a transport network, and then we have a core, and then we have a data center which belong either to the private cloud, is from the operator, or is from public, which is a can anyone can use, for example Google and Amazon. So you can see that this network is created by different component and also with different vendor. For example, the core can be you can bought from Nokia or some other Samsung. Transport part can be done by some third party. RAN can be come from Huawei, some other. So you can see that, and spectrum can be coming from your regulator of your country where you are belonging, and of course the customer is our end user. So you can see that this is quite complicated network, and it's very difficult for one operator to have all these components because this costs a lot of money and maintenance as well per year. So most of the operator hired by the third parties. And of course, if you are a quite rich operator like Vodafone, they have their own equipment all over the network from end to end owning. But again, the idea is here to show you that the solution which we develop is for this kind of network, and lot of innovation is done on the core part, which is the main backbone of the innovation in the wireless communication from 4G to 5G. Everything will be, and of course there is also innovation on the RAN part also. But if you really want to see the breakthrough in the innovation in 5G, 6G, and coming, that will be coming from the core part. They are enhancing core part to the limits. You can see in these slides. Okay, so the technologies which we work a lot in 5G starting 2014, 16, and back from the academia 2012. So we start with the various technologies according to the use cases which we got from the ITU, and then went to the 3GPP to finalize the solution for them. For example, for massive connectivity, we have technologies which shape us this domain. Then we have a capacity enhancement, and then we low latency and high reliability use case. So to fulfill all these three use cases, researcher, 3GPP scientists propose a lot of technologies. For example, massive MIMO, multi-connectivity, short latency packets, V communication. So these are the technologies which we use a lot. Of course, every technology can give you a certain band throughput, latency requirement, reliability. but the the highest amount of throughput, capacity, or latency will come if you decrease the distance between transmitter and receiver. So ultra dense small cell is one of the technologies which I think is really which really decrease the latency and increase throughput, because we are decreasing the transmitter receiver. The gain you achieve from ultra dense small cell is the highest than any other technologies so far you can see in this picture. Of course, massive MIMO can give you some gain, subtle gain, multiplexing in diversity, but if you really want high, you need to decrease the distance between transmitter and receiver. And of course, we have to 5G work below 6 gigahertz of frequencies, where they have used cellular, unlicensed, where they combine between both unlicensed and licensed, and also on the millimeter range frequency, 28 gigahertz, 32 gigahertz till 40 gigahertz. They work on the 5G. That is what happening in 5G. So most of you are already familiar with these technologies, and also in, of course, you wrote plot papers, and project is already available in these things. So what are the mega trend toward 6G now? So as Samsung wrote in the white paper that and with other vendors, that we need to connect machine as our main user, and then we have to use the AI tool, our wireless communication. Of course, we are using machine learning in the 5G, but here we have to go beyond what we are doing in 5G. That will I will going to explain you in next slide. And then we need the openness of the mobile communication. We do the openness in 5G, like we have virtualized core, we have open source core, we have SDN, slicing, we are doing that. But openness in the RAN part is not done in 5G, so that will be started already started in the name of Open RAN, Virtual RAN, ORAN. Lot of work have been done, and lot of operators are sitting together, and they are like the idea, and they break their business model, and they going to be an open RAN. So this means any software can run on any hardware, and any hardware run on any software. This means if you have a Nokia software and your base station from Huawei, it will be compatible, it will be run. But I will not talk in this topic about open RAN. Just to give you this, that these are the major trend. And then we have a social goal and mobile communication, because our society is now getting lot of apps connecting every devices. I mean, every day are creating thousands of apps, and we should be have some kind of standard where we define our social goal. Facebook is also working a lot on this, so this is still not standardized. So we have to define a clear borderlines where we can go, where we cannot go, because this is also a part of cyber agenda, cyber security of ITU, where they have to define our social goals along with other media tech information. So these are the four of the things which we seeing in the future. But today I will mostly talk on first two things because of the time constraint. Last two will be for the next presentation. Okay, to start with the journey, we reach to 6G. So we start with 1G to 6G. So let's see what will happen. After every 10 years, we have to shift our generation. So we are moving from one generation to another. The shift will be around in every 10 years. So if you see that in 1980, we start with the very simple network. On that time, it was really great because no one thought that we will end up with 6G. We have UPRANET, we have networks. They have a lot of devalued, and we have human machine interface, because we don't have any keyboard, mouse, or any human user interface on that time. Then in 1990, there's a big shift. You can see that. Please keep eye on this part. This is very important. APRANET now change into WW. So we start with a small kind of internet, mostly in state on that time. And we have a network, we applications start getting some important operating systems, some getting, and we have a nice human machine interfaces are available. And then in 1980, you can see that WW now turned into telco cloud, because a lot of operator now seeing the importance of internet, so they are start building the telco systems, and network getting a lot of important. This is the time where you can see ATM kind of networks available, synchronous, asynchronous, and a lot of work on that time is people are doing thing. And still mobile network is not so much popular on that time, but again we are feeling that it will be going to happen in next 10 years. So hardware are getting quite important because of Nokia's new set are coming quite heavy one. If you remember this one, 3320, and human machine interface get less value. And then after 20 years, the have you can see that telco system is now changing to cloud system. That is the main innovation. You can see that your phone interfaces and shape also getting changed, and network getting less important because you are putting everything inside cloud, and all the bottom boxes are also get valued. And then about 2030, so we need to change our hologramic kind of thing. So human machine interface will be changed into hologram kind of things. Your hardware will be mostly the RF part, because most of the hard baseband will be reside in your cloud, because your web cloud will change into data cloud center where you have different apps and DSPs are running, and network getting very less value, and lot of virtualization will be happen. So we are converging toward our communication with the computing world. That is quite important in the 6G because of virtualization. So if you see that the total domain is changing, the journey which we started in 1980 and we end up 2030, but of course not stop here. We don't know what will happen in 7 8G. So this is so far we have the target till 2030, and also 3GPP also start working on the future releases for 2030 target. So this is a nice picture I got from the internet, where I think it's nice to interact to show the differences between generation and the devices. If you see that the down is the input, we start with the numbers, arrow, T9. T9 means just to text messages. Then commentary, where you have BlackBerry, where you send MMS and this, and then text and voice, touch and gesture and tactile. You can see that the way we are heading toward the future generation. So this is the nice pictorial representation of the generations and the devices for each of them. So before start, 6G is very important. Why we are doing 6G? So if you see that from 1G to 5G, most of the time we develop solution either for our mobile devices or for the base station, either from downlink from the base station to the UE, or from the UE to the base station. So most of the time our end node is only one of the them, either base station or UE. And most of the time we create very short-minded approach, narrow-minded, where we develop a very narrow kind of solution where in things are fixed or mostly partially dynamic, which you can see in 5G. But in the 6G, we need to develop solution not only for the real world, but also for the virtual world. What this means that we have a digital twin of our each object. One real world is running outdoor in the real world, and other virtual world is running at your lab, research center, or at your company. So this means you need to optimize solution not for the real world but also for the virtual world. So the complexity will be increased, your computational resources will be increased, and your communication mechanism should be a different to fulfill the requirement not only for the real world but also for the virtual. The idea here is called digital twin, which I will going to explain you in the later stage. So here we need to talk mostly on very open mind, because we should be the solution which we develop is for the both world, and only the thing which is fixed here is speed of the light so far, which we know from the physics, but we don't know maybe speed of the light for electromagnetic wave can be changed in future, but for the time being it is fixed, and that's the way our electromagnetic wave travel in our physical world. Why we need why we need machine? Because machine can do everything which human cannot do. For example, human eye can see around 500 megapixel, but machine cannot. But machine can do more than that. You can create a machine which can do 1,000 megapixel per second. Similarly, there is other liabilities which human can do and which machine cannot. Machine can do better than that. For example, we can audible around 2000 hertz. We cannot go beyond that, but machine can. That's why we create machine, because machine don't have any physical bounding like human. As we our physical bounding by our birth. So the tool which is quite important for the wireless communication is the machine learning. So we have worked a lot on machine learning in 5G, where we develop different solutions. At mostly the solution is developed at the physical layer. And if you see the information which we are doing from 1948 to 2020, we use a very simple inferring communication model where we have a source transmitter, we add some noise, and then at the receiver we do some nice decoding to decode our messages, and then we destination. So this is a very flat one-way communication from source to destination. So in the machine learning, we have a source, same thing happen, but at the receiver we will get a feedback back to the transmitter. So we going to teach our receiver by getting the input from the transmitter to make a smart decision. So what this means, that this is the same thing happen, that you have a parent, you have a kid, so you can make your teach your kid for a certain age, for example 15. After that kid is smart enough to make their own decisions. So this means by using machine learning, you can solve a lot of problems. Your channel estimation, recoding will be quite easy. You don't need to get all the time measuring because you're already smart enough to make the decision. So this is the make big feedback loop which we get from the top. Of course, the machine learning have then different branches where you can use supervised, unsupervised, inference learning, federation learning. That is not topic of this presentation, but this is the main idea that machine learning can helpful for us in the future communication as well. So what is the difference of 6G machine learning with the 5G machine learning? First, we need machine learning because we don't have any accurate mathematical model. So that's why we relies on machine learning. Here I put DLD for the deep learning, you can say like this, but it's the branch machine learning as well. So in the 6G, we need to integrate both mathematical and DL kind of model. But again, there's no work have been done so far, but that is just the vision that we need to integrate both mathematical and DL model in our simulation tool. We cannot rely only on machine learning because of the computational complexity and consumption is too much. And then we need to optimize each or complete system module dynamically. But in the 5G, they optimize each module separately. So we have to do dynamically in 6G. And in 5G, it's non-intuitive, but here we need dynamically. And in 5G, mostly it's application specific, and here we need a target specific. In 5G, it's more on too many parameters. If I understand machine learning, optimization is quite hard in 5G, but here we need a dynamic. And of course, the problem with the 6G that, of course, the more computational efficient if you use all of this target. But okay, that is we need to figure out how we can decrease the computational complexity of the system. And the complexity in the DL in 5G is medium because the use cases is different. So this is the medium power consumption you need from the CPUs and other computing devices. So 6G mean quite interesting for the 5G, but 6G we need a thing which is not possible in 5G. For example, there is a lack of interoperability between devices because one machine learning algorithm cannot run on any other node. So there's a lack of interoperability, and also there is no open neural exchange where you can share that data, which make it possible to reuse the trained neural network model across all the framework. So this we need to figure out. So we need machine learning at your device level, at your localized level, or at your core part. And so this means we need end-to-end machine learning. So there is no module available in 3GPP so far which do this AI module in the core part, but I believe that will be a part of future releases where they will be do this kind of orchestration, management, data kind of analysis, data management, data orchestration. It will be all the part of AI when you do in the core part, and this is where the innovation will come. And the physical layer, we already work a lot in 5G, and of course now we are going to implement in the upper layer as well. So what the main idea here that what we cannot see in 5G, that machine learning cannot give the answer of why. If you tell the machine learning algorithm, the difference between cat and mouse, they will tell you very easily, but it will not tell you why it is cat, why it is dog. That's what we want to solve it, the answer why. So we need to give the answer in a why, that why why this happened. So this is quite difficult. It's not easy task, because here we need the help of not only communication, but we need a lot of computing tool like natural language processing, computer visions, where you have to try to figure out the answer of why. But that is the future we need to figure out. So what are the service classes and the scenarios for the 6G? So as I explained in the first slide, the main idea is to that we are going to a virtual world. So that is the main domain, that we are moving from our real world to the virtual world, where everything will be software defined networks, either in the core or in the day or in the access part. But we need to be in a virtual to make that happen in the 6G. So one the technologies which is quite important is the digital twin. Digital twin is not like our normal simulation. This is more like online kind of data, where you are coming data and you do all the data analysis it, and you can modify your model. For example, if your car is running at the physical location outdoor, and you have a one model running at your bulk and your mechanic. So this means you don't need to bring car every time, because your data is automatically coming and he going to optimize it. For example, if something happened to your car, he just update the software and your car working perfectly. And he can also analyze what will happen in next 1 month to the your oil consumption, your fuel consumptions, and some breaks, so you can easily. But here the main idea is to exactly the model each and every component of car into that computing model in your virtual space, and data should be coming online rather offline. This is the main difference between normal and you do a lot of data analytics on in the virtual domain. And similarly, you can do the digital twin of your industry and human twin. So this is be a quite future, but I don't know about this idea. This will be a 3GPP related stuff or not, but from the academic point of view and from the industry, automation is quite important, very much hot topic nowadays. And similarly, this is the same idea. You can also do a virtual twin of your whole city. Again, you need to model each and every building perfectly in your cyberspace, and with your all data analysis, you can update it online with the high capacity link, low latency, because depends on how far you from the cyberspace are, and then you do the all the data analytic and using machine learning technique, and you can really optimize your city with this tool. So what are the main target for the 6G? So I think we already have a great number of throughput already, because we are going to millimeter wave and terahertz. This is great, but the main idea is to decrease the latency. Latency is the main killer application for the 6G, as it was in the 5G, but emphasizes will become in 6G on our latency. For example, in the media, if you say we started with the text and then now we end with the hologramic communication, so latency should be very less to achieve this. So it's around 20 millisecond if you motion a photon time, if you considering that. And in this industrial internet, the latency should be around 25 microsecond to 10 millisecond about all the stuff which you are doing in this industrial environment. And for tactile internet, your internet of feeling, the latency should be around 1 millisecond, and for V2V is around end-to-end around 5 milliseconds. So I mean, you can see the divide, 1 millisecond from car to base station to the edge. So I mean, the main idea is to decrease latency. Whatever the use case is, the idea is to decrease latency, because that is the very difficult to achieve, especially if you want to do hologramic kind of communication, remote surgery, or communication. This is the main target to this. And of course, capacity is also important, but we already have very higher frequencies where a lot of bandwidth available, so that will, I believe, it will not be a problem. So spectrum is also one of the thing which is quite important for the network. I think this is one of the most important thing, because of that you cannot run any kind of communication mechanism inside your network, because this is called blood of your network. So nowadays, if you see that spectrum is mostly controlled by regulator of each country, that is politicized, also lobbying, so things, so where you have septum. So just to make a note here that Portugal and Malta is the only country in Europe so far which don't have 5G band auction so far because of COVID. All other European countries already have the auction for the 5G band. So in future, according to my view, that this cannot be a property of regulator anymore. It can be initiated by your network, it can be initiated by user, or it can be initiated by machine. But of course, this model, I don't know if regulator will happy with this model or not, but that is of course the vision. And then you have an open dynamic access model where you can dynamically control the spectrum, of course, with the help of machine learning, that in which city, which branch you need that spectrum, and what are the futuristic data analysis tool which can help you to divide that spectrum. Either you want to go for below 6, above 6 millimeter, terahertz, all depend upon your open access model. And that will be depend upon the geographical location. Either you want a narrow band, higher band, depend upon the physics of the waves. And of course, you want a dynamically regulated policies according to the power control, one of them. And we have to check if is initiated by machine. So we have to check if the chipset of that one available. For example, if machine wants 70 millimeter band, so maybe the chipset is not available. So we have to take care of these three boxes when you're going to assign. And then the sharing model is that it can be shared with mobile operator, can micro operator, virtual operator, satellite, end user, and maybe something else which I don't know yet. So the idea is here that can be initiated by anyone, any of the, this is not only human being, but can be network initiated machine and can be used by anyone. This is total different branch idea framework where we have dynamic spectrum management. This is my idea, but I don't know if regulator will again be happy with this or not. Okay, so past, present, future. So in the past, if you see that we started with the web application multimedia, and in there we have only two services, data or voice, where we need low latency, very less latency, because we don't have a problem with the latency, medium reliability and medium throughput. But in present, nowadays in 5G, we have three use cases. Everyone knows enhanced mobile broadband machine type communication, ultra reliable low latency communication as well. Here the use case will be different now because we have new use case coming with the tactile internet. So here we need a very low latency, high reliability and throughput. And what happened in 6G, again, the use cases are changing. We have more holographic kind of communication, new media. We need a teleports, lot of teleports you need, and you need new infrastructure. And there you need a hologram kind of communication with along with tactile. Again, very low latency, high reliability, and high throughput. So whenever we change our use cases, we come to the new generation. This is the main goal of this figure, that when you change a new, you have a new generation of them. So just talk more on 6G. So we are moving from 2D to 3D. We are moving from two senses, data and voice, to the five senses of human being. We want to transmit all five senses over the air, gigabit to terabyte, millimeter to sub-milli kind of latency we want. So for that, we need to follow this triangle. Huawei is already working a lot on this branch, and IoT also proposed the similar thing in their 5G workshop. New media, new IP, new services, and new infrastructure. So I will going to talk in the next few slides about it. So in the new horizon of 5G, you said that in the new infrastructure we need, if you can see the last portion of the circle, and from the inner circle, you can see that we need human-centric information in 6G. And then this is the various technologies on each generation. For example, from new infrastructure, you need integration of space and terrestrial network. Federated learning is very, very important. This is the one way you can decrease the computational efficiency of your computing, because every device have to compute their own data, and then you can do centralize and they can distribute. And then we have cloud PLC, programmable logic controller. and then we have trusted infrastructure. So these are the things which you can see in future with the different services. So about new hologram, with a new hologram, if you can see that that is quite interesting, that if you want to transmit the human image, is the 6D. So this means this human can rotate 360-degree and then the 3D direction. So this means it need to be quite fascinating, that the height and the width. So it depends upon the country. If you live in Europe, you have different height. If you live in Asia, you have different height. We need to create a pixel of hologram to transmit over the air. To do it, so far the study said you need around 1 terabyte per second. In the terabyte, just imagine you say terabyte and the bandwidth is around 2. So because you are doing in 6D, and plus this guy can do the 6 thing what human can do, 6 senses, which I will going to explain in the next slide. So to do this, to send the image over the internet of a hologram, you have to coming from quantitative digitalization to qualitative digitalization. What is that? In 1G to 5G, we mostly do the symbols. What we do, we can each and every byte have same significance. When you transmit your packet, and every byte have same significance. And if whole packet is retransmitted, if a byte is lost, that is the at the physical layer, at least we can do this. But in qualitative digitalization, every byte have different significance because we are creating a pixel. So every pixel have different value. So this means you don't need to retransmit all hologram if you lost in the channel. You just need to transmit only that byte. Why we need that? Because here latency is the quite important, and in another generation, reliability is more important. And these are the example of text and voice. You use this kind of model, and but if you hologram and VR, you use qualitative digitalization kind. So this is, you can see that we are moving from one digitalization technique to the different digitalization technique. And then services, let's talk about service. We started with the best effort services, we then deep safe services, but now we are now the teleport. So this is quite important for 6G because we want to send 5 senses hologram over the internet with high precision. This is also happening in 5G, but not so much frequently. But this is be a part of 6G as well, where you do the remote surgery with a very high precision. So that is the idea, that one is the human being and he need to transmit their 5 senses that can be voice, hearing, touch, taste, and smell over your location at your home, so your family can feel the same experience like what he's doing outside. For example, in the beginning, in the 1G, 2G, no one thought that we're going to transmit our MMS, hair, sound, and text, but that is possible. But and I also believe that this 5 senses will be possible in future, where you are transmitting over the air. For that, we need a very high throughput in term of terabyte. So that is just a number from maybe around 1 terabyte, 0.1, but around this, when you do the 6D model and plus the senses to sense, and also the hologram sub-millisecond latency. But again, we don't know the number because this is quite innovative and we don't know how much millisecond and throughput actually depend upon if you're transmitting from distance, depend from country to country inside city. So that is, but that is the idea. And then again, you can this is just a simple kind of example where you can see that if a Bob want to talk with Alice will talk with a Bob. You can encode it, you can transmit with the different kind of attribute. You can do light intensity, 3D audio, sound, texture, and you can even do the views of different angles. Start with 2 angle, 3D, 6D. So this depends on. So I mean, this is can possible, but again, you can do a step by step where you can encode and transmit over the air. So this is the more or less the difference between 5G and 6G. You can see that in the stack, network protocol stack, where you have network, you have transport, you have HTML data and application. Here we have total a new IP addresses, which I will going to talk now in the later slide. Teleports already explained you, qualitative. You need 5 matrices in your multi-senses, because here you need to create the metrics of this to transmit. This is talking here. And then you need the application data on the logic layer. So we need a new IP address, transport, and the hologram thing. So what are the requirements here? So if you see that in this table on my right side, you can see the difference between 5G and 6G. So the most important here that you can get the more new thing which you can see in 6G is this computational efficient system, because we are going to the virtualization. So computational efficient is quite important. Either you can do at the RAN part, which in terms of ORAN, or you can do at the core part in terms of network virtualization or software. So, but that will be a quite important for your efficiency. This is not available in 5G. This is my vision that it will be quite computation efficient. Of course, we need this energy efficiency, but energy efficient is already available in 5G with a lot of energy efficient technologies like massive MIMO is one of the very energy efficient technologies along with other. And also we need localization around 1 centimeter in 3D, along with other you can read it. So I will go a bit faster now because I have 1 hour, so I don't want to go more into detail, but you can ask question later on if you have. So computational efficiency is quite important, but the question is here how we measure it. Mostly we measure in gigaflop per second. The guys from the communication field like me, they have less knowledge of how you measure the computational capability. So computation capability is measured in gigaflop per second. So if you can see that if you want HD video, you need around 500 gigaflop. But if you want hologram, you need around 9,000 gigaflop per second. This will not only impact your CPU, RAM, but also the heat up your system as well. So we have to take care of all of them. And you can see that we are also moving from mobile GPU kind of stuff also, but that you can be find in later after in 5 year time. I think Huawei and Samsung working a lot on this kind of mobile GPU, where you have not only at your laptop but in your phone GPU only. The reason why they are doing, because the vision is that they have to end up with the hologram at one time, and this will be reached to this one. So you have to measure the gigaflop per second. So there's some architectural changes. If you start with the 4G, the idea was cloud computing. Mostly the cloud computing, the cloud and the core part doing a lot of computing part, and the communication is done only between UE and the base station, because our use case is very simple, only voice. And then in the 5G, you can see that we come with the idea of edge computing, where the computing will be done at the base station, core part, and cloud, and you can connect directly with your UE. This is our communication link, and the use cases will be different here as well. And in 6G, you can see that, as I explained you, that we have to combine with the computing and communication devices. That's very important. It's a convergence between computing and communication. So here we have a cloud. The part of cloud will be the part of computing will be divided between base station, core, and cloud, and also a part will be done at UE also. So we also do the computing of UE, but again there is the we have to define the use cases. So far we have this use case, but how it's done, that is the challenge. Because of related learning and computing of the resources, you have a lot of UE, you can combine the resources and send back. So, but this is the future where you can see that computing will be done all over the network. And then this will I will explain you later in the next slide. Keep it for that now. Okay, so what are the 6G candidate technologies? So one of the technologies, we start with the protocol stack. So this is a protocol stack which we have now. So this protocol stack which we are using from many generations, from 1G to 5G, and this protocol stack have a lot of problems. You can see that if you have some throughput and latency are not granted at the current TCP IP level, you have to create a lot of tunnels after tunnels to make this communication happen, and radio retransmission are not synchronized with the TCP overflow because they have to on different level. So we need to come up with a new protocol stack to break this boundary, and you can see there's a difference between fixed and IP. So this is my proposals, maybe my personal idea, where we are proposing I'm proposing that it should be in future like kind of flying protocol. So this means it can be created by UE or created by the network with the help of virtualized radio resource management. And on top of that, we are running our AI and dynamic blockchain module. So this means that your network can create your protocol according to the demand of your UE. Either you want holographic kind of communication, voice, other traffic, so you can make that possible. You don't need to be a fixed protocol in your network, but you can move around it. So it can be possible. Can we have a separate link layer from network layer? Why can't we have 5G, a new radio operator your home router without any carrier? These are all my question for the future. Assume a flexible access of your database as well. So these are some of the questions which I poses for the future. And for example, which I really want to see that no reconfiguration files we don't need a hard code addresses over the network. So, but again, that is the vision that we have to come up with the kind of client protocol which can run over the network and we can combine on the fly and we can use it, and with the help of tools like machine blockchain we can secure and learn our data analytics as well. And then we have to connect to X2X. This means we don't need to connect all the time with the base station. We can connect with any devices because of new technologies are coming like flexible antennas, RIs, reflected services, so we can communicate in any way to connect and to reach our goal. For example, if you want to talk with the base station, if there is a blockage, so he can talk from any route because he cannot wait. The latency will be main killer application. So this can be X2X communication over the network. So we can propose the idea edge is there for do you can mean do computing at very close to the UE, where UE can do their own computational and communication as well. And then the another direction is quite also I think interesting, where you can combine radar and the communication, because we know that radar is very good in sensing the environment, and communication is very good in connecting the environment. So we use the connectivity and sensing. Of course, it is possible to use the sensing from the communication, but it's very nice because radars are very specific for the sensing, so they can sense if user are close to you, user are moving, you can easily do the tracking. It's very good in the positioning also. So this is one of the things where you can combine radar and communication inside one chipset. Of course, they are available separately nowadays, but the idea is to combine into one chipset by using one waveform. This is the main challenge, at least at the physical layer. And then there's a convergence between terrestrial and the space network, where you can combine, again, the idea is to combine not only the ground, but also the space, where you have a different drone and mini satellites to have a connectivity all over the network. So this means the probability that all of these links are fails at once is very low. So this means you always have a high probability that you have a one link is available. So this is called massive multi-connectivity kind of concept, where you can enhance from dual connectivity to the massive connectivity connect, where you can connect at various time. And then we also need communication for the space, especially for the inbound passenger, because the internet is very expensive when you travel over the ocean, Pacific or Atlantic, or even on the ground. The internet is very, very expensive. So we have to come up with the solution, and also quality of service, which we achieve at the ground level, we should achieve same at the air as well. So again, we use the same computing and communication model. Like people start working on that. Boeing is very interesting on these. Airbus also, lot of Airbus deploying lot of base station only for the planes on the ground in Europe at least. So but the idea is to again to find the solution for the inbound, where you can have a decrease the cost of internet. So again, I mean, again for satellite, you can do the routing also in the space. Rather on the ground, you can do the routing, because there are a lot of satellites available nowadays. For example, on this table on the left hand side, you can see that wobbling, Boeing, they are deploying a lot of satellites. So you can do a lot of complement things up from them. You can, because they're LEO, GEO, and MEO. Each orbit they are doing a lot of orbits, so you can combine both of them. And the space internet, this is my idea, that I believe that in future data center will be in the space as well. Like Amazon, Google have a lot of data center on the ground nowadays, but I believe they can have a data center in the space. I don't know when, but this is, I think, one of the thing which is I want to see that that at least in the term of latency. And you can see that the Mars mission is going from the NASA now. So I will, in future, there is a lot of communication links over the space also. So it's important to have a data center over the space, rather they have to come all the way to the down. This is called space internet. New routing mechanism we need. We started with the packet switch network. Everyone studied in the universities. Now we move toward rail switch network. Again, Huawei is very working on them, and courtesy to them for this slide. So this is train by train, reducing queuing delay, deterministic guarantee. This is one of the qualities if you use rail by switch. And we are doing this, was doing statical multiplexing. Now we are going toward more computation multiplexing, and we need a new IP header as suggested by Huawei, that it should be a new field will come metadata and a command. This is a new area in the new IP address. So far IP address we only familiar with header and payload. We're moving from shortest path routing to the segment, and now we go for the preferred, because shortest path is not always good. We need to follow the preferred path routing, and some work have been done on this area as well. So what is command? What is metadata? This is quite interesting, because in metadata you have to give the name of the field. What is the metadata mean? So in the metadata you just specify the name of the object. For example, you want a secure message, just put the name of security and you can transmit over the network. And if you want VR AI kind of media, you just want which kind of experience you want to expectation. Either you want low latency, delay, or senses, you can transmit over the here, and also you put the measure. That is not metadata, I mean is the name of the field. So you can see that in future you can have a new IP address header, new field will coming, command and metadata. And also the idea of mobile terminal cloud. I believe that if you know the idea of cloud RAN, this is the idea of terminal mobile cloud, where you have your baseband is reside inside cloud. Your phone will be a simple RF, with the RF and some capability of low-level physical layer, where you have a part of HRQ there, and but your baseband will be staying. This is because of you don't want to decrease a lot of consumption inside your phone. So the cloud is going with you. Whenever you go cloud with you, they do all the computational and send back to you. I mean, as idea is same, that you do the computation will be done somewhere else, and then after computation processing, everything will come back to the phone. He will do and send back to. Of course, there is challenges there. There is a lot of questions available on this idea, but that is again my vision that this will be going to be happen. But again, the idea is to decrease your energy efficiency and to enhance the computational capabilities. And then to go to what high data rate of quarter terahertz is available. So we already a lot of bands available in millimeter, which you use a lot in 5G, but in 6G we are going to a terahertz, because most of these band are unlicensed band, and again the coverage will be quite less. There is a very specific use case for the them. Of course, if you want to increase the coverage, you have to do a lot of other techniques. One of them is multi-hop communication by using relay or reflective services. But most of the time they have very high links, so you can use either in your chipset, in your CPUs, where you have you can remove your cable. You just do the transmission using the terahertz in your Wi-Fi router in future, but not now. Then you QoSIG or your in-body communication as well. So of course, when you go for the high frequency, we cannot go for Moore's law anymore, because Moore's law tells us that the size of transistors cannot be decreased at certain level. So we cannot decrease more than 5 nanometer. The last transistor will be 6 to 5 nanometers. So we cannot go. So therefore we have to go into the optical domain. So in this optical domain, we have to go for the digital signal processing, but all in the optical domain. So you can see that you are after 2020, there is no more transistors, because of very high frequencies we are going towards in the optical domain. So as you know that we going toward the 300 gigahertz, so we need a component which going to have this capability of higher frequency. So below 3 gigahertz, you can use CMOS technologies. Is okay, no problem. But when you go above 3, you cannot have the same material, because for the chipset, the material will be changed. You have to come with 3V. in the chemistry, if you remember 3V, the periodic table, these are the material which are make that one: indium, metaphoric, and germanium. So that which we need, because this material have capability to bear the so high frequency. So 3V based transceiver in 6G and photonic based modulator receiver in plus. When you go beyond that, so you get to a photonic receiver. But you can see that for the takeaway from this slide, CMOS material will use for 2G to 5G in the transistor design, 3V for the transistor design for the 6G if they bear the capacity, and then photonic when you go very, very high frequency. So this is small just example taking from the one of the papers where they have very nice picture of the substrate of your chipset inside your phone. You can see that you have a lot of antennas because of milliterahertz. You have a lot of antenna available thanks to a small wavelength. And then you have CMOS and gymnasium based devices. These are material. And then you can see that there is the dielectric and the packing also available. So this is kind of chipset you can see for the 6G to communicate on the frequencies of terahertz. So also we need on the technologies on the antenna as well. One of the technologies which is Samsung is quite interesting in meta-surface lens antenna. So what happened in the meta-surface lens antenna, you have a phase shifter in the analog domain where you can save, but in the lens you have this ability. You can put DC 0 on one side and then you can put data on the other beam. So that concept is called the meta-surface lens. And another is called metamaterial. The metamaterial is that the material have this ability to tune it to your each element of your antenna, but you don't need a phase shifter here. Like here, you need a phase shifter. Here, you don't need phase shifter because all will be done on the domain at the metamaterial antenna. Another idea is reconfiguration intelligent services. I working on this a lot, so you can check it. So when you don't have any state line of sight with the devices, you put at the location where you have a line of sight with base station, and you can transmit to the UEs or other devices. This is called RIS, and this is a very hot topic nowadays. So there are some of the few scenarios which I define, I think, quite important for the future. So RIS can be one RIS board or massive antenna can work for different purposes. One, this whole block can go for EBVM, another will go for massive IoT, another go for reliable communication, depending upon the frequency you are sending from here. You can do RIS for the out of coverage. In coverage, sometimes you are out of coverage, so you can do kind of multi-hop to reach to the another UE. You can use RIS for the coordinated multi-point, like COM in 5G. You can make also coordination between different. So you have a UE with blockage with all of them, so you can divert signal and you can increase its signal by using diversity. And you can also use the multi-connectivity from different RIS. You can do the multi-hop communication by your RIS, and also you can put RIS over the cars moving object. This is more complicated because channel state information is varying quite a lot here, so it's quite difficult. But of course, that you can put RIS also. But I mean, every RIS have the different challenges, which I'm not going to talk now. Just this is scenarios for you. So, and also with the help of RIS, you can see that in 1G to 5G, most of the spacing between antennas are lambda by 2. Most of the time we use because of some specific use cases. But of course, in 6G or 6G plus plus, we can have uniform non-structured antennas. Uniform unstructured antennas, this means spacing between horizontal and vertical domain can be changeable according to the scenarios to create a different beam, narrow beam, high width beam, medium beam, depend upon the configuration of your antennas element. And on the Wi-Fi, also in the direction of Wi-Fi, there is another technology. Wi-Fi is also coming, which is quite high speed. There's also work done on this a lot, and you can see in future also a lot of LEDs at your home and also in your cars and buses and train where you can get your internet from the modulated light as well. So people working on this direction is also getting a lot of progress towards 6G. So this is a roadmap for the VLC. You can see that at the end of 2026, you can see a wavelength kind of multiplexing in the in the light domain. But now the idea is to reach around digital to light and septal multiplexing. So again, this is for the researcher who working on the VLC domain. And there is another interesting topics come in Samsung, and also few work have been done on this, or orbital angular momentum. This is mostly coming from the electromagnetic property of your waves. So in this, mostly we code our data in time and frequency domain, but there is a lot of angular shift available in electromagnetic wave where you can do a lot of modulation. For example, there you can use the spin of angular momentum. You can use orbital angular momentum by using different antennas element. You can demodulate your electromagnetic wave with different modes. So there is multiple orthogonal mode is available where you can model your data and you can send signal over the air. So this is also one of the thing which can increase your capacity along with your times, main and power. But you can also see here the orbital angular momentum concept. And then there is a quantum communication and wireless, which is also important. In the quantum, you can see that in the normal communication, you can send 0 and 1, but in the quantum, you are transmitting 0 and 1 together. A lot of work has been done on the wireline, but there is nothing will be done so far for the wireless, for the long range or short range. So here we need to do a lot of different transmitter design, channel, how it's varying. The decoding will be quite hard if you get error, because we don't know either 0 coming or 1. This is a state in quantum. And the molecular communication also, where you have the in-body communication, and is also help to analysis for the next future disease. And we know in the beginning if a guy have to be some disease or not. This is the part of nanotechnology where you do molecular communication. Okay, so for the molecular communication, the people who's not familiar, so this is some difference. So you can see that you have to inject something in your body, which is called nalomedicine sender, and your blood is the channel, and the organ is received is your receiver. So this is some difference. Like in wireless communication, you have a air, and molecular you have a human blood is your environment. In wireless, you can work with a light velocity. In molecular, you work very few. So this is a different domain. The difference between how wireless and molecular will work. And then also this is a brain to brain communication. So brain to brain, where you have do multiple brain together to solve the problem, and then you need to transmit is over the air, and then you go to all these base stations, signal processing, and over the air you can control from it. So this is be a very hot topic, because again very few work have been done on this area where you can combine medicine with your communication skill. And radar also, Wi-Fi, you can know how radar work, but we can also use Wi-Fi signal to detect the user if he's moving, if he's setting, because a radio wave can hit you and come back to the E node B, and then you can easily detect that if they are moving or sitting, everything. So that was, I told you that the 6C4, which is I think quite important nowadays. You can see that everything done inside one chipset: communication, computing, caching, and control. But I think this is quite important for 6G, that we have to do this more modular, heterogeneous kind of secure, where communication will be done at somewhere else, control will done caching and computing. So it should be divided over the network rather on the same place. On the private network is also doing a lot of research. So the in the private network, anything, any like industry, school, factory, hospital can create their own network, and all thing what you're doing in your globally can be part of your private network. And 3GPP is also working on this direction, standardization as well. For example, inside your factory, you can have your 5G new radio, you can have virtual RAN, virtual core, and you can only in your private property you can create the whole network. And here you have more interference limited system. Of course they can possible, but it is more easy that you can create your own network, and then you have a gateway which is just connect to the internet over another world. And you do the slicing also with a different portal orchestration. I mean, everything what you're doing outside you can do at your private network as well. And about channel modeling, I think it's quite important to talk on channel model here also, because the channel model which we're doing in 5G, at least we are doing ground to ground, but in nice in 6G, it's important to model all adaptively, air, ground, and in water, because we need to come up with the model which is more channel adaptive toward channel adaptive model. So the model which we are using now in 5G at least is static or semi static, and mostly we use either deterministic channel model, which is coming from the rate racing, or we use stochastic model. There are a lot of models available. So I'm not going to talk with them. So these are the model which is available in the literature. So you have a this blue where you have a segregator region, segregators, and receiver. So either we need to combine one of them, or we either we combine H with G with this, depend upon the scenario where you are on at that time. So these are the model which is available. So in the 6G, we have to come up with a more dynamically model, at least in the academia purpose, where we do more the kind of stochastic modeling approaches. So how we do that is a nice figure from one of the papers where you can do the channel modeling, then you have to do channel measurement, then you have channel characteristics analysis, and then you do the performance analysis. So we have to do two methods, as I explained in the previous slide. Either you do the rate tracing method, or you do the statistical channel model. This is quite good because it will give you a large scale search on the fading channel, and it's very good for the network planning also. But of course, when you do mostly on this more theoretically and more mathematical bounded model, you have to come up with a racer data, because they give you very small scale fading, and where you have measure your channel estimation and decoding. So these are the two branches, and these are the parameter which you can see the most commonly you can get it. So the idea is here is the following: we need to develop a channel model not for a fix, but which can cover all of them, cover all spectrum, all coverage, intelligence, and autonomous network, and security also. But again, channel model use a lot of matrix multiplication. So there is already a model available in the mathematics. So they are converting multiplication to the different domain where the complexity will be less. I don't remember the paper where they proposing that how you decrease the multiplication of matrix to the very linear kind of operation. So, but the idea is to make this channel more adaptive to along these frequencies. Okay, and then they have some optimization tool. So we work a lot from 1G to 5G on energy efficiency, supply efficiency. Mostly Shannon is very good, but in the for next generation, we need to work mostly on computing and communication. Very few. Actually, I never see any paper on this so far, but this will you can see that we have to study the loaded limits coming from the computing, and Shannon. Everyone knows about communication people what is Shannon is. And there is another trade-off. If someone want to work on this, they can also study that part as well. And then we have we use a lot of stochastic geometry tool for mathematics to model our system for 5G, but of course that is very valid so far also. But this another two set theory technologies, topology, topology, and logic theory. If this is quite heavy mathematics from the set theory, but this is quite important if you want to draw your categorize of your 6G network, or you want to define a topology. So it's very nice to study this two mathematical tool to make your 6G network to look into. Okay, so my idea for the 6G, because I just to give what is my vision. So I called my base station for 6G is human-like intelligent base station, like human can do. 6G enhanced new radio. So I just put E in front of NR because I believe this will be if 3GPP like they can put 6G enhanced radio. So what I want to do that I have a base station. I want to give the eyes to the base station, which I believe can become with the help of computer vision with the camera physically. My base station should have a brain like I have, and my base station can talk with the people like using a natural language processing. It's called semantic communication. So I will talk later on this slide. So for example, so I don't need any kind of complication tracking channel coding because I can see it. If I can see it, I can send message to the my base station, the brain, and he can see that, okay, this is a blockage, so he can hand over to the another base station, so he can get a communication to the this one. So the idea is that in the future, the base station, I want to give the eyes, talk, whatever I can do, my base station can do as well. So for that, one of the thing, the computer vision, everyone knows, I'm talking about semantic communication. What happened the semantic communication? Everyone knows Shannon. Shannon tell us that we can transmit symbol over noisy channel. Okay, that's very nice. But what is the meaning of the symbol? We don't know. Shannon never tell us that what is the meaning. He just tell us send the raw data, because that is the goal of that time on the communication. So, but in semantic communication, how we transmit, we need to focus what we transmit. It's very important. We need to know what we transmitting, not we just transmitting 0 1 0 1. We should know what is the meaning of 0 and 1. So that's why it's in 1926 Tesla said, if when wireless is perfectly applied, the whole earth will be converted to a huge brain. So this means we have to go from semantic communication towards semantic communication. So we have to break the limit of Shannon one now. So semantic communication have a lot of names: semantic communication, goal-oriented communication, online, and wireless. So I will not go into detail because of time constraint. I'm already over 1 hour now. So what is the main idea of semantic? So we giving a presentation layer, application layer very close to the physical layer. So we want to give to the meaning of the message. So what will happen with this? So with the help of this, you don't need to retransmit all the messages. You don't need to do complication thing, because you have a knowledge base at your receiver. You have a knowledge base as your data. For example, if I say a kid is riding a bike, if I transmit a kid is riding a bike, if something lost inside my channel decoder, like a bike, so he can easily take from the knowledge because he know the meaning of the bit. So this means we don't need transmit all the bit all the time. We just send a small bit and my receiver will be quite efficient to get the meaning of that bit. So the semantic decoder channel will be working very closely to our normal communication, but that normal communication is called semantic, and it's called semantics. The idea is that we are giving to the meaning from the application layer to the close to the lower layer. So what are the timeline and business model? So the timeline is around 2030. We can see the product of our 6G, but let's see. But that was the goal, coming from different group that we are reaching toward that time. But the 6G, and you can see the European Commission also start funding lot of proposal. FP9 call will be open with huge amount of money around 6G around 2026. So from 3GPP line, so for the guy from the industry know better, but this picture comes from 3GPP. You can see that we are around release 17, 18. So you can see that around 2029, you can see that around they are working. So you can see that 3GPP is far behind because they are from the industry, and the academia is more on track. So you can see that they are starting around 2029. So these are some of the thoughts for the next release, which is not quite important for this presentation. So business model for the operators, because this is quite important for them. The model which they are using is only one-sided. Mostly they take the initiative from the resource owner, then they go to the network operator to the user. They are taking a one-sided business model. So I will not go into more detail on this one as well because of time constraint. But in the 6G, there should be a n-dimensional model where there is an online all the time. You have a digital twin user, physical machine user as well, where they are asking thing, and you have a different business opportunities between all over the domain, and all will be benefited. So I called my network the liquid cloud network because liquid can take the shape of anything. So we don't need any boundary, anything. So this at device level, I need these specific abilities, and network level, I need this kind of ability. Technologies level should be like this, transport level and spectrum level. So these are some of the things which is, I think, quite important. And for the business model, it should be end-sided business model. Insurance company play a lot, and taxis from the digital twin, because we have human as machine, so machine should also pay that taxes. So and in the summary, so need high fidelity hologram, multi-sensory communication, terahertz, and pre-active AI communication for 6G. So, okay, we work a lot on 5G, so I think 6G will be quite nice for us as well. And this is a just difference from network 2020, which is coming from the ITU, and IT20 difference between two of them. So thank you from all of you, because some of the slides from our own, also from the GPP and also from Samsung and Huawei, and thanks to all of you. So you can ask the question now. Tamur, yes.
Yes, thank you very much. I think this is very interesting, and I would say that it is not one, you can say, seminar. You have covered a series of seminar, and
Yeah,
each
yeah,
topic can be expanded to a course or work item if we speak of 3GPP. So it's a lot of details, and you have given a lot of food for brain to digest. So since we are already over time, and
yes.
what I would suggest that our viewers, they can write us the questions if they have questions. I will pass them to Shahid. And also, Shahid has provided his email. So you can contact Dr. Shahid at his official email. That will be in the description. For future collaborations, if you're watching this seminar and you want to collaborate on any of the topic, I think Dr. Shahid is always open on establishing new collaboration and yeah, work together for new ideas. Anything you want to say to conclude?
That's okay. Well, thanks to Tamur and thanks to all of audience virtually which are there, and hope so some of you interested in the topics. You can please feel free to contact to me.
Thank you. Thank
Thank
you
you.
once again. And yeah, see you soon for another
Thank you.
seminar.
Okay. Bye bye.
All of
Bye
you.
bye.
Bye.
Bye bye.